Okay, I think we can get started. So, welcome everyone. Thank you for coming to the new season of the ICAL seminar series. It's going to be run monthly here at Imperial College London. This year, we are honored to have Sam Devlin as our first speaker. And Sam is a principal researcher at Microsoft, where he works on deep reinforcement learning for video games. And he's going to talk us about a very interesting topic about how humans and AI can cooperate in team play. And before giving him the stage, just to let you know that after the talk, we will have a catering session where you can talk with him or to know each other. And that session, it's going to be catered thanks to the sponsorship of DeepMind. So thank you. Stage is yours.
Thank you, Bo. Thank you for the invitation, and thank you everyone for showing up today. So today I want to share a little of the journey our team are on towards building an AI agent that can play games with anyone. I think it's important to just take a pause before we get into this to reflect on the fact that all of the work I'll show today is a team project. Most of it won't be my own. It's the result of these amazing people up on the screen, all our former interns and colleagues and our external collaborators. They've done some amazing work that has greatly inspired all of the thoughts and things that I'm going to share with you today. If there are any mistakes, they're probably my own, so call me on them, right? I'm here to learn from you just as much, right? So please do call me on the mistakes you see. As much as we can make this interactive, it's a small enough room, then I'm really up for that because it can be a bit more fun if we have a bit back and forth right late in the day. So our team are the Deep Reinforcement Learning for Games team at Microsoft Research. We aim to advance reinforcement learning to enable new applications in modern games. And in particular, we look at empowering game creators with new tools and capabilities so that they can create entirely new ways of play to entertain billions of players worldwide. This mission leads us to think about questions in this space of reinforcement learning a little different than some typical approaches. So hopefully this will raise some new thoughts about how you might apply your own work. One of the key research challenges that we particularly think about in that space is multi-agent reinforcement learning with human players. Okay? So given the naming of this talk series, I'm kind of assuming everyone is familiar with the typical single agent reinforcement learning space. Not everyone? Okay. Won't matter too much because we're going to assume we have this agent that we can place in an environment that observes the state, takes actions, and maximizes rewards at a time. There's a lot of good methods out there for this when this agent is alone in the world and nobody else is acting in that world. When we start to put multiple agents into that same environment, it becomes a bit more complicated because we need to coordinate with those that are around us. And we see a particular challenge when those people are human players, right? We want to actually put these agents into games with players. We can't expect to know exactly how that player is going to play, how they're going to adapt online, how they're going to change. And we can't have our agents learning online at the same time, taking billions of time steps, because no human player is going to stick around and wait for that to converge. So the particular challenge that this sort of comes down to, if we try to break it down more, is ad hoc teamwork. So I'm assuming we have a way to train a team of agents to play well together. Okay, this is from the multi-agent learning literature. We can train a team to play well together. We might train another team to play well together, but there is no guarantee that if we try and match those two agents, that they'll play well together. Even if you've got two really good agents that play well in teams, they won't necessarily play well on the same team. Even if that agent is an exact copy of the other agent, but trained with a different random seed. You set off two exactly the identical agents, train them separately, and then try and match them. They won't necessarily play well together. This was proposed as a challenge in this 2010 paper by Peter Stone and colleagues at AAAI as the ad hoc teamwork problem. So how do you do collaboration without pre-coordination? And more formally, this extends the normal multi-agent MDP objective, where we try to find the policies that maximize accumulated reward. So the typical RL problem, but focused over multiple policies. And it extends that to include an expectation over the other possible agents. Conveniently, this does retrieve a single agent problem again, but we now have a few extra details to work out as to how we're gonna tackle that. So overall problem is how do we collaborate with anyone, shown by this. It's going to be broken down much simpler into what's the policy we're trying to learn, what are the policies we expect to play with, so the human players in our case, and what reward should we maximize. This is going to be the framing of the talk. I'm going to step through each one of these in time with some proposals on how we're thinking about tackling these. But this is the core problem that we want to talk about today. Any questions on problem setting? Anything not clear there? A little early, maybe. So maybe someone's coffee is going to kick in. Okay, so I'm going to start off with the policy we're trying to learn and how we see a way of creating an ad hoc aware agent. Okay, so the particular agent that we proposed in this Amos paper, this work led by Louisa Zinkerab, was the Melba agent pictured here. So this is the neural network architecture that we're training. We assume we've got a set of agents in this case to train it with. And then we're training this model across, we're using meta learning to train this across a set of different teammate agents that it can play with. Again, this can be broken down a little bit more. So first of all, we observe the behavior of the other agents in our environment. This can be done online whilst the agent is learning, as we did in this paper, or we can train this embedding off of a batch of past data, such as replays of human players from public servers. The network architecture then includes an information bottleneck through which these observations must be compressed, right? We want the minimal representation of the other players. So essentially we're in a POMDP, we're seeing what we can about the other agents. We're going to try and compress that into a smallest representation that we have possible. This was heavily inspired by work that we had done previously in a NeurIPS 2019 paper that showed that these variational information bottlenecks were particularly useful for improving generalization in single agent RL. So we brought that particular structure into the network here. So we observed the other's behaviors over time, and from that we tried to predict the future actions. We made an assumption that we could just independently predict each teammate. The main thing here is that we are not conditioning anything on those predictions, right? This isn't a model-based approach where we predict what the other person is going to do and then respond to it, because there will always be inaccuracies in those predictions. Instead, we just use the loss on those predictions to shape the representation that we do condition our policy on, right? So this is an additional loss that we can use to try and inform what the learned representation is and has to compress it. Some of the other things we took here, we tried to take a structure that would both consider what the agents, the other agents type might be, and how that might change throughout time within a single episode. So one of these gets sampled once per episode, and one of them gets sampled every time step. There's a particular assumption. This was based off of the machine theory of mind paper from DeepMind, and we took that one forwards. Again, could be some experimentation there, but the main thing is we're trying to learn a representation where we can quickly recognize online how the other agents in the environment are playing, and then we condition our policy on that. So we both condition on the state that we're in and our current belief over what the other agent in the environment is, right? Again, we also use that variational bottleneck to try and capture some sort of form of the uncertainty. Could be some opportunities there to improve how we're modeling the uncertainty. The main thing is that you then condition the policy and the decisions the agents make in the environment on based on your current belief about what the other agents in your environment are. If you are highly uncertain about what the other agents in your environment are, then it might be useful for the agent to learn to take action, information gathering actions, to learn more about its teammates. Or if it's in a particularly critical stage, it might just try to act on behalf of the team anyway. But we don't use the predicted future actions because of those potential errors in them, right? So we're just learning a internal representation to condition the policy on. Okay. So that's the overall agent. To make this a little clearer, I want to consider a simple example. So we have this ad hoc teamwork coin game where these two agents are collecting coins to take to the various banks. Blue coins get more if you drop them at the blue bank, red coins get more to take to the red bank. The agents are supposed to be working together to try and get collect as much money as possible. But the other agent in the environment, so ours is the little one down in the bottom left, The one on the right, we don't know how that one particularly is acting, right? We had a whole set of these that our agent had to be able to work out how to best respond to. Some of them might like red coins, some of them might like the closest coins, some of them might like blue coins, right? So our agent has to learn to recognize them. So when it's deployed, it has to recognize quickly online based on the observations of what that agent's doing, what type of agent it's currently playing with, so that it knows how to respond to that particular agent. So we compare this against arrangement methods. The gray dashed line is essentially the typical sort of model-free approach where we have no structure within the network architecture. It's just a feed-forward policy. And essentially, it's learning a best response to all of the agents it's trained with. Here, you typically end up with an agent that's playing a very safe policy, right? So it's maybe just always collecting the blue coins and depositing them because that gives it some sort of return. But it's not actually coordinating with the other agents in the environment. It's not recognizing who it's playing with. The green line is a previous meta-learning paper, so this RL squared method. Essentially, we've got a recurrent policy now. So this is trying to learn, is taking in those observations and conditioning on the past observations of others, but no particular structure with like the auxiliary task of predicting other actions that we had. And then finally, the pink and purple ones that get the highest score are our agents that are trying to keep that model of the agents that they're playing with. We can look a little deeper as well to just like see if the representations are actually helping here. So what we did on the next stage, just to look a bit closer, was at various points during training, we froze the network that we had trained. And we did linear probes essentially of the learned representation to see if you could predict the class of the other agents from the learned intermediate representation. And we see that over time, the Melibur agent is able to correctly classify the agent that it's playing with and to a much higher level accuracy than the just recurrent policy alone. Okay, so that's our agent. That's the policy that we're trying to learn. But that agent assumes that we have a set of agents that we can train with, right? So this works if you are just trying to train with a whole bunch of different agents and you've got a version of those agents to train with. But we don't have that necessarily for human players. And as I said before in the sort of motivation, right, we don't expect to be able to just deploy this agent and have and test with human players and learn online with them. So instead, we want to try and start to model the policies we expect to play with. One piece of work I took a lot of inspiration from on this is some nice work out of Berkeley on the game Overcooked, on the utility of learning about humans for human AI collaboration. So at one extreme, you could just generate every possible policy that you might ever play with and train your ad hoc aware agent to recognize and best respond to all of them. That's going to work if your game is tiny, right? For Coin Game, maybe we could have done that. For Overcooked, I think it starts to get questionable. And for the scale of games that we're looking at on Xbox, then it's just completely inconceivable that we would generate every possible policy to best respond to. So much like the Overcooked work here, we start to assume that we have some data on how humans are playing this particular game. And we're going to use that to build models of human play as a proxy for us to train with, right? The Overcooked example, I think, nicely showed that, like, if you do self-play with too small a population, you get this example in the top left where they're not coordinated. So the agents that train together would play well together. This is exactly a problem of the sort of ad hoc teamwork setting where that agent is now playing with an agent it didn't train with. They're running into each other. It's fine if one of your agents is learning, right? Your human player can just figure it out and just get around what the AI is doing. But we don't want our human players to adapt to our AIs. We want our AIs to recognize our human players and work with them, much like the two examples on the middle and the right, which were trained with a behavior cloned agent and is able to recognize and respond to both types of policy that the human player might play. Yeah. We started doing a bit of work with Berkeley after this, in particular looking at how do we do a deeper level of evaluation of those agents. So for this, you could just look at reward curves like I did in the Melibur example, but it leaves out some of the extremes, right? And those extremes are very important to us because even one experience of running into the agent will break the immersion for our players. We really, really want to recognize those extremes. We want to recognize where those experience breaking moments might be for our players. And so in this ARMAS 2021 paper, we propose concretizing some of those particular edge case scenarios into unit tests. And we keep these as unit tests for evaluating our agents. Engineering approach, but it's a very useful tool for us to go beyond just a reward curve, right? The reward curves hide so much, right? They're great for seeing that average, that you can capture some of the variance, but you lose a lot of what's happening within that variance, and particularly the extreme cases. And that kind of motivated a line of work around really looking closely at how people perceived our agents. And so one particular study that we ran was this human navigation Turing test. So this is in a game called Bleeding Edge, made by a Microsoft game studio called Ninja Theory, based conveniently very close to us in Cambridge. And in this, we isolated a very simple task of an agent just having to navigate to a space, right? This is very intentional so that people could study these tapes back and forth, right? So we're randomly matching human data of humans moving through the 3D space with agents, and then randomly showing them to people via an Amazon Mechanical Turk study, and asking which is more likely to be human, right? So in the full study, people had a lot of time, right? They could take their own pace, they could scrub back and forth through the videos, they can interrogate them. You're only going to get to see a clip on the small thing, but I will ask some people if some thoughts here, okay? So we will make this interactive one way. This is really intentional though for trying to understand how people actually think about these agents, because a lot of past studies have run this where you play and interact with the agent. And then in those sort of circumstances, particularly as this game is very high paced, when you play the full game, it's 4 versus 4 online arena game, there's a lot going on. Players are under a very high cognitive load, so it's hard for them to assess an agent. Whereas in a study like this, we give people the time and the space to really sort of interrogate and nitpick about every little thing that the agent does wrong. So I'm just going to put this back and ask the question. Any thoughts? A or B? Hands up for A, being the human. Okay. And for B? For B. So B was the agent in this particular case. And in this very first study, we found, state-of-the-art RL agents can very reliably learn to navigate, right? This is a single agent task, which is navigating from point to point. We could reliably get them to train. The dashed line is the approximate human time. So we had a bunch of human data on how humans would run through this maze. And with some training time and a few tweaks, we could get a deep RL agent to reliably run to the goal. So they can learn how to do it well, but when we actually put it in front of human users, they could always tell the difference, right? So hybrid and symbolic here are two of the agents that were in this ICML paper. The fact that every dot on there is a particular participant and the percentage times that they got the decision right. You see there's a whole bunch of people that could 100% of the time tell which was the agent and which was the human, right? There's only one person that got a little confused on the symbolic one, but for the most part, people could easily tell the difference, right? There are key differences. If you just set off a standard single agent, deep RL agent to maximize time to goal, it will create non-human-like sort of behaviors in there. We dug a little deeper, right? There was a whole qualitative analysis of free text where people try to justify why it wasn't a human. And some of the ones here that were particularly easy for us to pick out were things around like the frequency that it made mistakes, and this jerky physical movement, right? So it was quite a jittery agent. So trivially, we can just do some reward shaping with that domain knowledge, right? And we can make the agent confuse people, and that worked so well, right? We get to this side on the far right where people are kind of confused, right? It's right, the mean's around 50%. Yeah, people are muddling this up with human play, but it's very domain specific and it's right down to that specific instance, right, of just navigation. So the much more sort of general approach is to blend in some imitation learning. And this is actually a combination of methods that I have real growing confidence in for a lot of reasons. I think the two learning objectives really complement each other well, right? in reinforcement learning, we try to optimize that reward. And then when there's a tie break on things, typically people are having some sort of entropy regularization, biasing things to maximum entry policies, and you get all this really random behavior when everything is good, right? So I did this previously for a card game. We deployed, it was actually an MCTS agent in that case, and we deployed it in the game. And at the point where the agent worked out that it won the game, it would just start throwing cards around, right? Which players hated because they might not have yet perceived that they'd won or lost the game, right? So if they have perceived that the outcome of the game, then this looks like an arrogant agent that's just throwing its cards around, dropping that it's lost, or just being arrogant that it's won and throwing its cards around. Worse, because this was also game had a collaborative element, player was like, what's going on? My teammate has just started throwing cards around randomly, right? So here, and in that example as well, we blended in some imitation learning, and we got an agent that was both more human-like and equally as good at the game, right? So it's a nice prior to have this imitation learning to break ties in your reinforcement learning agent, so that when you need to, you can get sort of human-like behavior. And it's also handy for the imitation learning, because when you do imitation learning purely offline, once you actually deploy that policy, the agent will often get off distribution, starts acting randomly because it's not seen this in the data set. And so having some reinforcement learning training as well can help smooth that out, so you get good behavior in the areas where you don't have human-like examples. And then once it gets back onto a space where it's in human examples, it can come back to the human-like side. So we applied that to the navigation task, and we get this PPO plus IL agent, which is shown here. And now we get an agent that was judged more human-like than humans by the majority of humans that were judging it. And it was a nicely, this is a broadly applicable approach, right? There's nothing domain specific in here anymore. There's no reward shaping for the particular thing. We just rely on that assumption that we've got some human data. So this gets us one policy, one human-like policy for us to train against, but we wanted a whole set of them, right? We want to be able to train our ad hoc aware agent to best respond to all possible types of human play. So this is the point in talk where we're going to have a large change of pace, and I'm going to stop advertising the stuff that we already did, and start sharing some of the questions that are currently going through our heads, some of the challenges that we're seeing. Hopefully, maybe this is the interactive part now or over the food. But yeah, this is essentially an open invitation for your direct feedback today, or as an open opportunity where I see there's a lot of gaps here in the literature where there's opportunities for people to do new research and make great contributions. In particular, so we're thinking about that case of trying to learn the set of agents to train with. Human data is not agent data. This is a really common assumption in so much imitation learning work that just assumes that trajectories are generated by a single policy, that policy is fixed throughout data collection, and the policy is an optimal reward maximizing agent. None of this holds when you have a very large scale human gameplay data set, right? Our trajectories are from millions of players worldwide, right? They're all muddled up into one space. Yes, we might be able to identify that they came from a particular person, but that person is going to keep learning and adapting. Even within the time frame of a single game, their policy is not fixed. And we also, because it's in the wild, have no guarantee that that actually is the same person, right? People pass controllers around, people share accounts, people had a bad day, people get distracted during the game. We had one complaint today that there's a whole bunch of data where the player just stands still, right? These are things that we have to try and disentangle when we work with real human data. But maybe the standing still one isn't like the super interesting research question. We need to, crop our data. But we do want to represent every single way that human players are going to play the game, right? If we remember that ad hoc teamwork goal, we need the expectation over all of the policies that we're going to play. It's not enough that we can imitate one that's imperceivable from human play. We need to imitate all of the play styles that the agent is likely to see. And so when imitation learning work just uses these trajectories from a single previously trained agent, you lose all of this, right? Because you have this assumption in the data that it's all from that one single policy, and you're just trying to recover one policy. I've lost track of the number of papers I've seen that conclude that a small MLP is sufficient to reproduce, to imitate a particular set of trajectories, right? That's fine if you know that your data was generated by a small MLP, right? If you know what your data was, the function that generated your data, then yes, you can use it to fit it. But we don't know what the function is that generates human gameplay data, right? So we have this big entangled mess of different trajectories that are non-stable and not necessarily reward maximizing. So I want to share a few sort of insights. So we're expanding now to the full game, and we're looking at data from about 16 years of gameplay data. And so this is a top-down view of one particular map. It's a heat map. And we see where the players have been going, right? And the main thing that's just highlighted here is just right at the beginning of the game, there's a very key decision to go 3 different directions, right? And even in the same state, absolutely same state at the beginning, people will make different choices based on preferences, based on what's going on around them, you know, and they're distinctly multimodal. Right, so a lot of approaches which with behavior cloning will end up trying to learn an average policy. Might work out okay here, right? They might still just run down that middle track, but we need to also capture the cases when humans go off to either of those sides. So this is a really important one for us now, and something that we're looking at a lot now. And I think this would be really easy to study as well with agent data, right? So you can make mock data sets that cover this, right? Don't just take a single agent's data set. Mix in a bunch of them, see if you can recover all of the policies within that data set. And the second one, and this is work particularly led by Ida, Guy and Kimya from our New York lab when Guy and Kimya were visiting, looking at the fact that humans aren't necessarily reward maximizing. Even in a very, very competitive game like this, right? We see that when we embed all of these trajectories down to two dimensions, we see that the reward on the left doesn't shape the space at all. There's no clustering based on the score that the players are getting. It doesn't explain anything about the different trajectories that are created. But fight or flight does, right? Whether people are engaging in a fight or trying to back off from it, that clusters human behavior a lot more than just reward, okay? So maybe you could argue this in like a domain-specific way. There's a particular reward around fighting or flighting, but it starts to show that, you know, reward in this case isn't the only thing. A single scalar reward like the team score is not the only thing that's explaining the human's behavior. So how do we capture that? How do we understand how different players are playing and capture that from the data set? Which leads to the final part of the talk. Let's assume that we can model all of those now. And instead assume that we both have our ad hoc team aware agent we talked about at the beginning, and we have a population of human-like agents to train it with. So the final thing is that we now need to optimize something with this. Right? So if I go back to the original sort of motivation here, we made an assumption that's common in the literature that we're trying to maximize some accumulated sum of rewards. Right? This is really convenient because it means we can use single agent reinforcement learning approaches. But I think it's this particular assumption comes from this problem being stated out of the reinforcement learning community, and that being a set of tools that we know well. If our humans aren't playing as reward maximizing agents, why should the agents that play with them? What should the agent, once we've got an ad hoc aware agent, we've got a population agent, what should that agent even actually be trying to do? Should it be trying to maximize the team score? Should it be trying to empower you to maximize the team score? Or should it be doing something completely different? So another question, interactive moment. Which teammate would you prefer? Right? So I give you the choice. You're going to play with one of these agents. One of them is a really good teammate and you'll win the game every time. and one of them is a really bad agent and you're going to have a bad time and you're probably going to lose the game. Which agent who prefers to play with the green agent on the left that makes you win the game all the time? Yeah, a lot of hands for that. Who wants to play with the terrible agent that makes you, yeah, one. So you see, we're different. Some people like this, right? I bring this up, not, I bring this up because this is how most studies in this space are done, right? Something in the middle, maybe? Yeah, it's something more than just winning, right? There can be a lot more to playing with it. But this is how a lot of these studies are done. And I'm not going to single out any papers because I don't think that's good practice, right? But this is in so many papers where they're like, here's one agent from the past literature. It's a terrible teammate. Here's our new agent. It's a fantastic teammate. We ran a user study and users preferred our new fantastic, wonderful, shiny agent. End. That's not really informative, right? 90% of the people like the nice, shiny new agent that makes them win all the time. What I think is far more informative is this, and there's a really nice paper here, so I will highlight good practice, I think, from this NeurIPS 2021 paper of comparing agents that are both good, right? So if you've got two agents here that are both just as good at the game, and they both work just as well in a team amongst themselves, now which one do you prefer? Who wants to play with the agent on the left? Who wants to play with the agent on the right? Can't really answer this, right? Because it's far more nuanced. If they're both just as good at the game, right? Once we get to this point where all of the agents are good at playing the game, then we get into a far more nuanced conversation about what do you like about the game, right? Do you want to play with the agent that's going to maybe try and sabotage you? Do you want to play with the one that's somewhere in between the best and the worst, right? Far more nuanced. And this paper is really nice, right? They look at things around like how much did people build up trust with the agent? How much could they interpret what the agent was doing, right? Much deeper dive into what was the player's experience playing with two equally good agents. And I think that's the exciting space, right? We're going to get to a space. Hopefully you believe the roadmap from the first two sections of. We're going to get to a place where we can create an agent that can play well with anybody. But the real fun bit, I think, is going to begin when we try to think about what are the experiences that should start to enable. It's kind of the last point that I have here, and I think this is the biggest question, right? So I think if you want to go after something that's super high value to contribute to this field, is what even is the goal here, right? In competitive games, we have this really nice and clear moonshot goal, right? You defeat this human champion, you have your superhuman AI, you're done, you walk away, right? But in a collaborative game where we're trying to empower players, it's not as clear cut. And maybe that's part of the fun, right? We get to explore this space and we get to explore lots of different sort of scenarios where we empower players in various different ways, right? So we talked a lot about the agents being embodied physically in the same space, but acting as a separate agent. We can also look at shared autonomy settings where this is actually players and the AI controlling the same character. And we could study that in itself for how that empowers players to more people to join the community. We can look for the agent that deliberately sabotages you in fun ways. We can look at things in between where you've got a sort of a more back and forth. But yeah, I think it's a lot less clear what that grand goal would be, what that grand challenge is. I'm really hopeful that we can discuss this over the snacks and wonderful break. If this has piqued your interest in ad hoc teamwork as a problem overall, really recommend checking out this workshop we ran at IGCAI, mostly ran by a group in Edinburgh and Austin. All the recordings are available on YouTube from this, so you can get a good breadth of all the other things that the people in the community are doing beyond our team. And in particular, some of the workshop organizers wrote this recent survey, which again really starts to specify the breadth of this challenge, right? The original 2010 paper showed that this was a challenge, and now the survey really sort of opens it up and shows how broadly the community has started to explore this, all the different particular instantiations that come up when you think about things like shared autonomy versus embedded space versus zero-shot coordination, and all of these different particular flavors of ad hoc teamwork. So if you've been interested in the particular problem, I recommend these. And if you want to hear more about our particular approach, then there's my details. Let's talk. Open to any questions or discussion throughout the time afterwards. Thanks.
So questions from the audience or from online people? Feel free to shoot.
Yep.
Are there any studies rating human teammates? Maybe there's like some, you do some data analysis on what human teammates.
Yeah. So the question was, are there any studies on human teammates and how humans work well?
Like what preferences humans have for other human teammates, basically.
Yeah, preferences amongst humans for different teammates. Yeah. So I'm particularly aware of, I believe her name's Evelyn Tan, she's an Iggy PhD student out of, I think, University of York, that's done a lot of study in this particular space, right? Because again, video games can be a really powerful tool for studying teamwork, right? So human players are regularly put into teams online with people they've never met before. So it can be a good tool for studying how humans do ad hoc teamwork. It can also be a good way to study how very well formed and highly functional teams, if you go to esports, right, and see how those teams work together. Again, it's different extremes, but yeah, so I think Evelyn Tan would be one connection into that space. Yep.
Do similar problems arise when agents are no longer teammates and are in fact adversarial, or is it?
So the question is whether similar problems arise when in
agents
competitive
not
games.
really working.
Yeah. So if the game is purely adversarial, like if we're talking 2 player 0 sum, then it doesn't matter, because all we have to do is assume the worst case of our opponent and play a best response. If we play the best response to our worst opponent, then anything that the opponent does that's less bad will do better. That works for 2 player 0 sum, right? That can make us win. Games like poker and stuff, then yeah, you might still want to try and infer who your opponent is, because then you can eke out more cash from the table. Similar sort of approach can be applied, right? If we try and infer who our opponent is, condition our policy on it. So it can be, but yeah.
Right, and then the Amos paper, you mentioned that the agent might take actions to try to recognize the other agent's behavior.
Yep.
How would you incentivize that? Is there a reward for that, or?
No, so it's not directly incentivized other than trying to maximize team reward, but it's in the network structure, because we try to capture the uncertainty in the intermediate representation. We have both like a mean and variance on our current belief over the other agents. Mm-hmm. Then you're then it's something you're conditioned on in your policy, right? So you could be in a state where you have high uncertainty. If you've been in a state with high uncertainty before, and this state is safe, maybe, right? So chilling out here on the bench, right? Safe state, highly uncertain who my teammate is, then information gathering actions will just be optimal for trying to get towards the team reward, to try and reduce your uncertainty about your teammate.
Because that's not part of the architecture, is it? It's just
the uncertainty. Whether you need to recognize your opponent as a part of the your teammate as a part of the environment, mm-hmm. But the part that's in the network architecture is that we're trying to capture that uncertainty, right, and then condition policy on the uncertainty as well as our current estimate of what they are. So it's only rewarded by the team reward still, or whatever objective we choose to maximize. But it's in the network architecture to try and capture an uncertainty. In the bank game, we did see that. So let's go back a bit. In the coin game that I showed, I think we found that the uncertainty wasn't as, no, this was the hierarchy actually. Then it made less of a difference because the ablation and it were performing the same. So there's an element of how much do you need to know about your teammate in a particular environment. So that can change it. But the way that it's essentially in there is probably better without the highlight, is the fact that we condition on both mean and variance, which was our estimate of trying to keep, our approach of trying to keep some uncertainty measure over who our teammate was. I think there's huge opportunity to improve this, right? Like every single part of this, we're going to attack.
So basically what you're saying is like by making the variance smaller, you're better off at playing the game.
In some cases, yeah, and in some game, and so this is where the environment makes a difference, right? So in some environments, reducing the uncertainty over who your teammate is will be beneficial for maximizing team score. In other environments,
That leads to the agent taking actions to
gather more information, and in other environments, it might not, or maybe it's even just like particular states. If you're in a really critical state. So about to save the ball in a football example, because a lot of this gets done in the RoboCup examples. Save the ball. Doesn't matter what your teammates are doing, right, or who your teammates are at that moment. You need to stop the ball going in. You do that regardless to maximize team score. Once you're then out just in general play, then maybe you start to take information gathering actions. It's also where I think it's interesting differentiation to a lot of the zero shot coordination work, in that we really take a temporal aspect, right? So we're focused on games that have real-time games, long sequences of actions. We assume there is a little bit of leeway where we can feel out and try and learn something about our opponent, our teammates. Whereas if you think more to the Hanabi saying, it's very critical that you quickly identify who it is with, right? So you might play a little safer because every card play is essentially, it's harder to do that sort of communication and finding them out. So this is where I think we lean towards a more taking some time to recognize the people that you're playing with, rather than zero shot need to coordinate.
like the fees and figure out MVP before you actually start playing, right?
Yep, and Louise's previous work is very bad. This is essentially very bad, but in a multi-agent setting. Like, and one of the names for it previously was another pun on very bad, but we didn't go with that version in the end, unfortunately. But yeah, this was bringing that experience from very bad forwards into the multi-agent setting. I think this one was first.
Can an agent learn good human teamwork, I guess, working with a human by considering games where lots of humans are playing together?
Yeah, so we haven't explored this fully, but I think this is a really exciting direction. So for the question was, can an agent learn how to be a good collaborator of humans from watching other humans collaborate well with each other? Yeah, and I think this is a really exciting one that we might now see, right? So we have this data set of 16 years. We're trying to model all of the ways that different people play in that space. Some of those players, as you said before, some of those players are going to be good teammates. They're going to be good ad hoc teammates. They know how to just drop into a game with anyone. We can identify who those good teammates are. Maybe we can do away with this and just have an annotation learning agent that's going to do it all. It's possible. It is possible. I haven't found it yet, but it is possible.
In regard to the question you mentioned, because most of the time playing online, the collaboration between players is not that ad hoc, because people have all means of communication. They're talking to each other through or they know each other from like real life.
Yep.
So there might be some part of the behavior that just analyzing traces of the game you won't be able to capture, because you have to look at other aspects of like the coordination problem.
Yep. Yeah, so questions around like if that there's other information that we can't observe, that players are talking to each other in channels that we can't capture here. Yeah, no, it's absolutely true. And I think that's why we might see this multimodality in human play, right? If you just consider the raw state from the game looks exactly the same. But yeah, they're talking to people either on the games chat. We do not monitor any of the games chat. We do not capture any of that data. We have no access to any of that. So yeah, even if it was in-game communication, we wouldn't know that's how they're coordinating and causing that difference in action. So that's something we've got to try and infer. And it's also like the exciting sort of next steps, right? One exciting next step that I didn't talk about, communication. Right, communication is absolutely critical in these types of games. People talk to each other when they're playing these games. That's how like if you play well in these games, it's almost entirely via people talking to each other. So the very exciting one, and we're talking a lot with our Montreal office about this, is about how do we do sort of language condition policies in these types of spaces. And again, I think it comes nicely round to that sort of question about what sort of experience, right? If you tell an agent to go to base A or attack base A, and the agent knows that's not the best thing to do for the team right now, should the agent ignore you? Should the agent do it anyway because you told it to? And I think that, again, that's a really fun space to play in as to what sort of reactions do we want from an agent? Does it change in the fact that we know it's an agent? Would it change if there were two teammates on, two human players playing with two agents, right? How should they respond to it? I can't imagine a time anytime soon where we allowed natural communication back because of where that might go. So it would purely be behavioral what that response is. And so then it's going to be a real challenge in someone tells an agent to go to base A and they don't go to base A because it was better for the team or better for you. Maybe they stepped in to save you when going to base A could have left you abandoned. How do we communicate that that was the right thing for the agent to do in the moment?
Something like it's different. This one.
Yep, go for
it. Making you modeling the behavior of the cooperative agents you play with, the agents that you're trying to cooperate with. Doesn't make you more susceptible to overfeed to the behavior that you're seeing during training?
Yes.
Like for instance,
Yeah.
in poker, if you have like doing this theory of mind thing that or multiple, you think that I'm gonna do this, or I do the opposite, and so on.
Yeah. So the risk of overfitting to just the ones you've seen during training. So I
think my question is if it is increased by actually modeling the behavior of players and not adapting on the fly, like in zero shot. In theory, if you model, it's like modeling the environment. The more you know the environment, the more your policy is overfitting to that environment. Same thing happens here, but like with players in environments, station, right?
So you're talking about specifically in the agent architecture modeling.
Yeah, modeling the other will make you more prone to overfeed the players that you see during training.
I think the biggest thing is going to come to this part, right, as to what do you actually have coverage of the full policy space? Because if there's a mismatch between the distribution of policies we train with, right? So if we haven't done this bit of modeling well, then I can see that being more of a reaction. I guess the other thing maybe that we've tried to do to counter that a little bit is we're not using in the agent, we're not using the same model as we try to generate these from. We are trying to compress as much as possible. But that could still have a risk, right? That if you haven't seen that particular type of agent, you're going to try and push them towards you're going to try and encode them into the space of policies that you've seen before and then best respond to it, which my opinion was. Yeah, it's an interesting, and I think it's part of the like this becoming potentially more cyclic. So I think about this in terms of like Dagger from imitation learning, right? We put this agent out there, players will respond differently. Some of them will just outrightly attack the agents, right? We'll essentially get our adversaries. Maybe we should have that in our population, like some particular adversarial agents to increase our population that we train with. But yeah, probably more of an iterative approach. But I'm not sure the zero shot ones get around it, right? Like,
so what's the shot?
Yeah, okay. Cool. I think, is there anyone up?
You mentioned that there was inconsistency between I just wonder if it is helpful to consider some psychology factors when calculating the reward.
Yeah, so great suggestion of human behavior isn't correlated with reward alone. So you can consider psychological factors as to designing the reward. That's kind of precisely the angle that we're going at here with. So Ida's background is more from the cognitive neuroscience side. And so that's a large part of where this type of analysis of the human data came from, is trying to really understand what are the actual motivating factors for humans playing this game. So in this case, going down to fight or flight, but we're also looking at other sort of broader aspects of humans' motivation for playing the game as to how that might be formed into different reward functions.
So how do you measure fight or flight?
So great question. How do you measure fight or flight? So domain specific, we look at when a player is within space of an opponent,
Okay.
and it's looking at do they engage in the fight with the opponent? So do they move towards, do they actually try and attack, or do they move back? So it's quite domain specific of breaking it down for that particular game.
So in like team scenarios where how does that work? Like, because teamwork is cooperative as well as like destructive. So
Yep, really good observation. So this looked at individual people, whether they were engaging or not. One of the other aspects that they were starting to look at was, is this person not engaging because they're trying to regroup with a teammate, right? So what particular reason for whether is it they're running from the fight, or is that because they're regrouping with teammates? Are they engaging with the fight because their teammates are there? So yeah, there's much more to do here to analyze how much of the behaviors that we're seeing here are social.
Yeah.
There's a lot more to unpack there.
How did you do the dimensionality reduction here?
Yeah, so so this is UMAP off of the trajectories. There was some summarizing of the trajectories. So to do with, in particular, there's a whole line of work that IDA is really leading around task sets and trying to recognize when players are trying to achieve certain tasks. So the trajectory is essentially summarized by the tasks that a player is trying to do at a particular time, which gives us a fixed left vector that then gets UMAP down to two dimensions.
Also, there's some like design, like hand design.
Yeah, there's again, that's where it gets quite domain specific to take that trajectory and try and map it into what they're particularly doing, which is again where we can start to label things like fight or flight.
I've been trying to formulate this question for some time.
Okay.
Well, I'm going to try. What is the main goal for the agent? Because an agent can either be just some helper to full-on human, but as you said, the reward is not just get most points, it's have fun or troll or do anything. Yeah, how do you have any specific direction you're going, or?
So I think it's the same struggle I have in formulating this slide, right? But it's a really good observation. So yeah, we have some certain angles that we're going to take with this. For the team-based game, we probably will look at maximizing team score as the first one. So the agent tries to push the ball.
Yeah, I suppose because a sort of an actual use case is, let's say a user disconnects, you can have some more, okay, that is a bit difficult because then you can claim that, okay, maybe we kick that person so an actual useful bot can go in. But yes, I guess one way is to, okay, introduce an actual agent that can do something.
Yeah. So yeah, maximizing team score seems like at least an easy way to avoid the breadth of experiences that we might want to go to. I'm very intrigued by things more around empowering the players, maybe as a more general concept, rather than just win the game, like make them win the game. But yeah, that really is that sort of nebulous space, I think, of like, there's a lot of different directions this could go. Does start to get applied, but I also, yeah, the hope is that, I don't know, I think this really, it's exactly the same struggle, right? So, and I think the community is also in that sort of space, right? So this challenge was originally proposed largely out of the sort of RoboCup literature and about people playing pickup games of sports, so that if people can drop into a game and play a sport with anyone, why can't agents? More recent examples, there's been a lot around Hanabi, but I don't think Hanabi is, personally, I don't find it quite the right match game, because a lot of the games we work with are real time, so have the sequential element. Overcooked has been coming up as a particular one, but again, that leads to just this team maximization score. And I don't think that's the fun in Overcooked, right? Like just playing with the agent that makes you win, or the big green button that's just win. win now, please. That misses the whole point of Overcooked. Maybe we can't play those types of games with agents. Maybe there isn't a way to recreate that social aspect and that back and forth. But it's a fun place to explore and try and make fun agents to interact with.
Okay. Well, last question.
Sorry.
Yeah.
Do you ever envisage like agents learning what individual users like? So the idea that rather than kind of setting an objective, like whether that be cooperation or maximizing some sort of reward, you kind of learn from player data what each individual player likes.
Yeah, and I think that's a really, really strong angle, right? That we could, this maybe gets us towards an agent that can play well with a whole bunch of people, but then over time we want to like fine tune it towards what do you like, what do you want from your agent or your teammate. It's also a really nice thing of, so one of the things that I've been challenged with being at Microsoft that I hadn't thought of coming from the game AI community before, is that a lot of people think a lot about a single game and the AI for that single game. But when Microsoft own an entire platform like Xbox, we can think much longer term about a particular player, right? Recognizing how you play particular games, what types of games you play, right? And build up that sort of profile of someone to then bring down to your particular AI that travels with you between different games, rather than necessarily just being the Overcooked agent that makes you win Overcooked. Really recognizing, fine tuning. But again, there's lots of sort of privacy issues and things that we'd want to think about as to how to do that. Like, how do we set that just so that you have your particular variant rather than that be more broadly across. But yeah, really fun space there.
Okay, so just before, for the people here in person, we are going to have some food now. But in case some of you leave, we're having another session on the 12th of October with Felix here about grounded language learning. Thank you very much for coming.